Continuing on in section 3.2 here, feel free to pause and give this a try. So to solve here, we could solve the top equation for x and get integer coefficients and constants, but that's still going to take quite a few steps. So instead what I'm going to do here is I'm going to recognize the fact that 8 plus negative 8 gives me 0. And I'm going to go ahead and add up these two equations. So negative 2x plus 5x gives me a total of 3x. Positive 8 minus 8y's give me 0. And negative 8 plus 12, again, we add both equations up in their entirety. So I add my x's, add my y's, add my constants. Here I get 12. Solve for x by dividing by 3. And x is going to be 4. I can take that 4 and plug it into any equation that has both an x or a y to find my solution. I'm going to plug it into my top equation. Negative 2 times 4 plus 8y equals negative 8. Add or subtract first. Keep in mind, guys, that just equals 0. And that's fine because when I divide to get rid of my multiplication here, I get 0. And that can happen. We can plug it back in and check. Negative 2 times 4, negative 8 plus 0 gives me negative 8. 5 times 4, 20 minus 0 gives me 20. So we know we're right here with 4, 0 as our solution. Sometimes at first glance, our equations don't look like it's going to be easy to solve for a variable and use substitution or to eliminate. And so we're going to have to multiply each side of the equation in a system of equations by the same non-zero number to create equivalent systems. And we can use this to help us create opposites in order to use elimination. So this is going to be our go-to when it doesn't look easy to graph, it doesn't look easy to use substitution, and we don't have anything to eliminate right away. We're going to create something that does, like in example 4 here. So we're going to find the solution of the system of equations. 2 and 3 are not opposites, and 7 and 5 are not opposites. So what we're going to do is we're going to create opposites. I'm going to look at 2 and 3 and figure out what number I can multiply to get them to be the same thing, like finding a common denominator, for example. So 2 I can multiply by 3, and 3 I can multiply by 2, and that gets me to 6 for both of them. Keep in mind, however, I need opposites, so I'm going to multiply one of them by a negative so that I get opposites. So I'm going to multiply my equation with the 2 with my x to be negative 3, and my 3 equation by 2. And when I do that, I distribute it all the way through my equation. If I do something on one side, I have to do it on both. So here, for my top equation, I'm going to get negative 6x minus 21y equals negative 12. And it wouldn't have mattered which one we made negative here. That doesn't matter at all. Okay, I could have made my 2 negative or my 3 negative. Just keep in mind that we have to have opposites because when we add these, we want it to get to 0. Same thing on the bottom, I'm going to distribute. So I'm going to have 6x plus 10y equals negative 10. Do a real quick check here. Did we change every term? 2 became 6, 7 became 21, 4 became 12, 3 became 6, 5 became 10, negative 5 became negative 10. Perfect. Everything's changed here. Now, I have something that I can eliminate. So I can go ahead and add them up right away. Negative 6x plus 6x gives me 0. I get negative 11y equals negative 22. And once we get to this step here, it's the same as we did in the last example. We solve for a variable and then substitute it in to solve for our second variable. Multiply first to simplify both sides. Add or subtract, then multiply or divide. So here my ordered pair is negative 5, 2. I could have done the same thing here with the 5 and the 7. So I had a 7 and a 5. multiplied the 7 by -5 and the 5 by a 7 to give me -35 and 35, which gives me 0. I just used the smaller numbers, so I'd have to distribute with smaller numbers and work with smaller numbers. Doesn't matter either way. Okay, but -5, 2 is what we're looking for there. Now, feel free to pause here and give this a try if you'd like. Again, looking at this, it doesn't look like it's going to be easy to graph or use substitution, so we're going to try and use elimination. I don't have opposites to start with, but I can get them. And some of you might have done this with the x's. I'm going to do it with the y's just because I did x's last time to show you it doesn't matter which one we do. So I'm going to look at my 7 and my 2 and figure out what I can do to get them to be opposites. Well, if I multiply my 7 by a 2 and my 2 by a -7, because again, it doesn't matter which one is negative as long as one of them is, I get 14 and a -14, which are going to give me 0, and that's what I'm looking for. I'm looking for them to add to 0. So I'm going to take my 7 times 2 and my 2 times -7. And when I do that, I distribute to the entire equation. If we change one piece, we have to change the entire thing. So I get 6x plus 14y equals 30. And I get -35x minus 14y equals positive 28. Double check both your numbers and your signs. So my 3 changed, my 7 changed, my 15 changed. Those were all positive. On the bottom, my 5 changed and changed signs, my 2 changed and changed signs, my 4 changed and changed signs. So make sure that your signs and your numbers, that's a real quick place to check to see if you forgot anything, because it's going to be a lot easier to fix it there than it is to try and track your mistakes down. There's a lot of stuff happening in these problems, so you want to make sure you're thorough as you go. So now we can add up our equations because 14 minus 14 is 0. I get -29x equals 58. When I solve for x, I get -2. Now that I know what x is, I can find y by substituting it into either equation, doesn't matter. 5 times -2 plus 2y equals -4. We're going to multiply first, add or subtract, then multiply or divide. So my ordered pair here is going to be -2, 3. And again, we can check that by substituting into the original equations and make sure that the solution we got works for both equations. Here we're going to find the solution of the system. If we look, we already have opposites, so I'm going to go ahead and add these up right away. -3x plus 3x is 0, and y plus -y is 0. So on the left side here, all I have is 0. On the right side, -5 plus 5 is also 0. When I get something like 0 equals 0, what that tells me, guys, is I'm not going to have any particular solution that's like a 2, 3, okay? Here, I'm going to have infinitely many solutions. Not just one. I'm going to have infinitely many solutions. This is telling me that my equations are actually equivalent. So this is like a dependent system where our two lines would land on each other. Not all solutions, but infinitely many. If it works for one ordered pair, or for one equation, it will also work for our second. And that's because we got a true statement here. 0 equals 0. On B here, again, I have opposites, so I can go ahead and solve right away. 4 plus -4 gives me 0. -6 plus 6 gives me 0. But 6 plus 10 gives me 16. Does 0 equal 16? Nope. So since 0 doesn't equal 16 and I have no more variables, I know I'm not going to get an ordered pair as my solution. I'm actually going to get no solution here. No matter what we do, there's not going to be anything that works for both. These lines are going to be parallel lines. They don't necessarily look it right now, but they're going to be parallel. They're never going to cross. We're going to have no solution because what we got is not true. It's not conditional. It's not an open statement or anything like that. It's just not true. 0 never equals 16. Feel free to pause here and give this a try if you'd like. So at first glance here, I don't have opposites. I could maybe graph it, but I'm going to use substitution. I'm going to solve for my y here. So I'm going to add an x. And again, we could have multiplied to get equivalent systems and then used elimination, but I'm going to use substitution here just to show you guys how that works as well. So I have y equals -2 plus x. I know what y equals, so I'm going to take what my y is, substitute it into my second equation. We distribute, and when I distribute, don't forget that I take the sign with my number. So I get 2x plus 4 minus 2x equals 0. Combine like terms. 2 minus 2 gives me no x's, so I have 4 equals 0. So when we use substitution, we still get down to a statement that is either true or false sometimes. Our x is canceled. No more variables. So we look, is this true or false? 4 does not equal 0. So here it would be no solution. And again, we could have done the same here. If I'd have multiplied the top by 2, for example, -2x plus 2y equals -4. And then eliminated. -2 plus 2 is 0. 2 plus -2 is 0. And I get -4 here, which still is not true. So you can use elimination or substitution there. I just used elimination to show you how that would work. When you use elimination or substitution though, make sure you plug it into your other equation. If you plug it back into the original equation, you'll always get 0 equals 0 if you did it right. And that's not what we're looking for. So make sure you always, when you substitute, use the second equation. Feel free to pause here and give this a try if you'd like. I'm looking at this and I'm going to say that elimination is going to be the way to go with this one for me personally. You can solve for y here fairly easily and use substitution, but our numbers are fairly big, 12s and 18s, and we're going to have to multiply by 3, and it would just be easier for me personally to get opposites. So if I look at y and 3, here's a 1, remember? So if I multiply the top by -3, that'll give me my opposite that I need, which gives me -12x minus 3y equals -18. And then I'm going to put these two together. You can rewrite it if you want to. There. Now that I have opposites, I can go ahead and add. 12 plus -12 is going to give me 0. 3 plus -3 is going to give me 0. So on my left side, all I have left is 0. Everything canceled out, but remember that still means we have 0. On my right side, 18 minus 18 is also 0. So here, I have a statement that is either true or false because I have no variables left to make it possibly one or possibly the other. 0 does equal 0, so that's going to be true. Since it's true, our solution is that there's infinitely many solutions. Any ordered pair that works for our first equation will also work for our second equation. Quick recap here for section 3.2. A system of equations can be solved by writing equivalent systems until the value of one variable is clear, then substituting to find the value or values of the other variable. If the equations in two systems are equivalent, then a solution of the system that is easier to solve is also a solution of the more difficult system. And that's all I have for section 3.2. If you're still unsure about solving systems here with substitution or elimination, you can check out in Algebra 1, sections 6.2 and 6.3, I have videos, and there's a few more examples and a couple more things to look at, so that would be another place to look if you're still kind of unsure after this section. Again, that was section 6.2 and 6.3 in Algebra 1.